Thank you for attending my presentation on the paper Selective Palladium Catalyzed Amino Carbonylations of Olefins to Branched Amides. The main goal of Liu and his team was to convert a terminal olefin into an amide. We know from organic chemistry that when you add something across an unsaturated bond, such as an olefin or an alkene, the substrate or the thing that you're adding can either end up on the less substituted side or the more substituted side of the alkene. This will result in either a linear product, which is when it adds to the less substituted side, or an isoproduct, which is when it adds to the more substituted side. Liu's team was able to create a mechanism that creates almost exclusively isoproducts. When we're talking about isoproducts, we mean this form of a product where you have your alkyl chain sticking down, your amide off to the right, and you have one lone methyl group sticking out. That methyl group makes it a isoproduct. There were some difficulties with previous works with doing similar reactions. They had limitations. The first limitation that they faced was that the amine had to be weakly basic in order for the reaction to take place. So these systems typically are composed of a palladium metal ion with some ligand system in a solvent, and there is acid introduced. If you have a strongly basic amine, the amine ends up deprotonating the palladium ligand proton complex, deactivating the catalyst and preventing a reaction from proceeding forward. This reaction scheme, for example, was created by Jimenez and his team. And what they used was a phenolic or an aromatic amine. We know that when a nitrogen bonds to an aromatic ring, the nitrogen acts as an electron donating group, so electron density is pulled away from it, and the lower electron density makes it a more weakly basic amine. Jimenez's team and other previous works were only able to make these reactions work when they used weakly basic amines. Secondly, their selectivity in their products was almost completely linear. So we can see here we have a linear chain of an alkyl group with a alkene on the terminal end. And the product is, again, a linear chain with an amide that is also in a linear formation. So these are the main differences between previous works and the present work. Liu and his team in our present work was able to use stronger basic amines, and they were able to create almost exclusively isoconformation products. The metal product or the metal complex used is a palladium with two monodentate ligands. The ligands are 2-diphenylphospheno, 1,2-methoxyphenol, 1H pyrrole ligands. Palladium is a D10 system, meaning it has 10 d electrons in its oxidation state of 0. And prior to being able to catalyze the reaction, so first, the two ligands add to the palladium in a dative or coordination covalent bond, which means that the lone pair on the phosphorus of this ligand acts as a Lewis base, forms a bond with the palladium, two of them. Before we can actually catalyze the reaction, a proton needs to bind to one of palladium's lone pairs. This forms a conjugate acid with a positive charge. We spoke earlier about strong and weak bases. This is where strong bases tended to give us some trouble because they would abstract this proton, thus deactivating the catalyst. However, Liu's team, because of the ligands that they used, they were able to use stronger bases without deprotonating their catalyst. So this is the mechanism that I showed earlier on slide 2, but I'm going to go through it again because it's an important mechanism for understanding what's going on in the reaction. So we start with a palladium metal with 2 halogens bonded to it. These halogens are displaced by the ligand, and then we add our proton to it. So we're now ready to catalyze the reaction. First, the unsaturation of an alkane with a terminal olefin will form an alkene bond or an alkene coordination bond with the palladium metal. This olefin will then insert itself between the palladium hydrogen bond, forming an iso product that is bound to the palladium. Carbon monoxide is introduced, and it also inserts itself between the iso group and the palladium, forming this compound. And then finally, our stronger base amine will break this bond and form our product. We then regenerate our palladium with 2 ligands bonded to it, and once they find another proton, they are ready to start the reaction over again and catalyze another cycle. But what we end up with is an isobranched amide. A few analytical techniques were used in this paper. The first one being gas chromatography. So gas chromatography is a thin tube through which there are 2 phases, a stationary liquid phase, which coats the inside of the tube, and a mobile or transient gas phase. This is usually an inert gas, such as nitrogen. A sample is injected into the transient phase, the gas, and it travels initially at the same velocity as the gas. However, the compounds have interactions with the stationary phase. And this is the amount to which they interact with the stationary phase is different for every compound. And the amount that they interact with the stationary phase will dictate how quickly they move through the tube. So if they interact more with the stationary phase, naturally they'll go through the tube slower than something that doesn't want to interact with the stationary phase. So what you get is if you insert a mixture, it will slowly start to separate out. And you get readings at the end whenever something other than the inert gas passes through. What the researchers used this for was they were able to tell the relative selectivity of their product mixtures. So you have an iso or a linear conformation that was produced. Well, if you pass your product mixture through a gas chromatograph, on the other end, you'll get 2 peaks, a linear and an iso, and their relative heights will tell you relatively how much linear versus iso product you had made. The second type of analytical technique was a mass spectra. Now, these are normally paired with gas chromatography so that you can insert a mixture, separate it, and then analyze each component individually. But this graph on the left shows an example of a mass spectrum. So over time, as the different compounds go through the gas chromatograph, they will enter the mass spectrum machine. First, they are charged. So in some way, they are imbued with some charge. And then they pass through a magnetic field with a given trajectory and momentum. Based on the mass of that compound and the charge imbued on it, it will change its trajectory in a magnetic field. Like I said, the different masses of the different compounds will change their trajectories in different ways. And the machine can measure how big of a difference its trajectory change, and it will give you a mass overcharge result, which can be correlated to just the mass of the object. So this is used for characterization. What was our products on the other end? You can see these peaks that each of them have defined products coming out, and it tells you what the relative mass of each of these products are. So you can characterize in some way, what is this compound based on what mass does it have? And then finally, they used proton and carbon-13 NMR spectra. What these do is they show the different chemical environments of the carbon and hydrogen atoms. So in a way, if you are a carbon atom on this alkane chain, somewhere in the middle, you'll say, I'm bonded to 2 carbons, and each of those is bonded to another carbon. But if I'm this carbon right here, I would say, oh, I'm double bonded to an oxygen, but I'm also bonded to a nitrogen, a carbon. So in a way, every carbon or every proton in the molecule will see a different pattern of elements connected to it. That's what we mean by the chemical environment. So we can measure how many different chemical environments there are for each proton. And this is what we see here in the bottom right, different peaks representing different chemical environments of the hydrogens and the carbons in the machine. So looking ahead at what sorts of research can be followed up on in the future. So we talked earlier about Jimenez's team, which was able to show when using weakly basic amines, they could get linear products. Liu's team in this present research showed when using strongly basic amines, they could get iso products. Well, naturally, the first 2 things that come to mind when we're thinking about future research that can be followed up on is creating linear products with less basic amines and iso products with more basic amines. What these would do is give chemists a larger toolbox with which to synthesize different compounds. Another idea is doing similar catalysis with alternate metal centers. So maybe instead of palladium, we use copper or some other type of metal center that might be more widely available or more inexpensive or more easily to scale up in industry. And the last idea about what future research we could pursue is catalysis with command selectivity based on reaction conditions. So perhaps there's some combination of amine and ligand or metal center and ligand that allows us to have command over the selectivity. If I turn up the temperature of this reaction, I can get linear, but if I cool down the reaction, I would get iso products. Some sort of command over the reaction conditions. This would be easily applicable to industry or other forms of scale up where a wider variety of reaction schemes would be necessary for creating different compounds. These are some ideas of what research could and should be looked at going forward from Liu's research in this paper. These are my work